So I'm Paul Melis. I'm from SURFsara in Amsterdam. We're the Dutch National Supercomputing Center located on the Science Park. Close this one. So as you'd expect for a supercomputing center, the core business is providing compute services for the universities, but also a few companies there. And the whole thing around supercomputing, data storage, networking, etc. We also have a small visualization team. Myself, I consider myself a 3D nerd. So this is the cave that we used to have at SURFsara, which is like a cube in which you're standing with the glasses on and you can see things in 3D. Well, we don't have that anymore, but it was a lot of fun to work with. So my background is computer science, but I specialized more or less into visualization early on. So the SURFsara visualization group is small at this point, 2 people only. Currently looking for a third because we were always 3. So we have a bit of a specialty, so I'm a bit more into the 3D animation. My colleague is more into the interactive web-based visualizations, Unity, stuff like that. So we support our users on the infrastructure that we have, so the supercomputer and the clusters, which means providing documentation, providing ways to do remote visualization, which I will show a little bit later on. We maintain the software stack that's on these machines, so peer review visit and all the tools that the users want to use. We also like to be a little bit of an expert into these tools, help the users with making decisions on file formats and the best options, etc. And we also give courses on visualization. Once or twice a year we try to do a visualization project for an end user. So this is really a software development thing where we create, for example, a small tool to do, for example, visualization of genetic data sets. At some point we had a virtual supermarket application, which was a research tool in a game engine to run around with a virtual cart to do research in. So all kinds of different stuff. Because it's very visually attractive, we usually get asked for PR and things like that. And apart from more the hands-on stuff, we also like to keep track of all the nice things that are coming out in terms of visualization devices. For example, the Microsoft HoloLens or augmented reality that you can do with an iPad. And I'll show at the end of my talk a little bit of that, what is interesting to keep track of. So I figured I'd ask you some questions. I don't know if you know this Mentimeter tool. So if you grab your phone or your laptop, that works as well. Go to menti.com, enter the code, and we can do a little survey. All right, so the first question is, what do you currently use visualization for, if at all? And you have, I think, 100 points that you can divide over the answers any way you like. And I'm curious to what the answers are. Right, so the first answer is in. So the menti.com, and then use the code. That should be it. No login otherwise, no registration, whatever. So we have somebody that does not use visualization yet. You have some work to do. Okay. What's that? Yeah, it is. Good. Right, so, sorry.
Is that a free service?
Yeah. Yeah. At least it used to be. I'm not sure if it's still, because this is for my company's account, so it might be paid by now, but it used to be. 14, I think we have about 20, 25 people. So, okay, so interpretation, analysis, exploration, that's good. It's kind of what you expect, I guess. Here you see the duality, right? Using it within research or using it to communicate is there. So that's definitely shown. Debugging, I would expect that maybe be a little bit higher, because if you do some kind of simulation, how are we going to check what comes out, if it's correct or not? A little bit of PR. Something else. Who answered that and what exactly would that be? Anybody that's filled in something else? No? Okay. Any surprises here for you? For me, it's, well, I kind of guessed it's what I would expected. But. Right. Okay. We'll move on to the next question. And these are a few statements, and you can indicate if you agree with these, yes or no. And the way these are written, of course, is to push you for a certain answer or not. So visualization provides insight that non-visual types of analysis cannot provide. It doesn't contribute much to research, or why bother, basically. It's the second statement. It's becoming more important as data sets grow in size, and you don't really need interactive 2D or 3D visualization. So I guess you got the first one right. No, but when we agree on this, right? This visualization provides things that you cannot do otherwise. That's an easy one. I like seeing this one because we usually see visualization being all the way at the end of the stack, right? You have to do a paper first, you have to write, you have to do code. You usually don't have time to do the visualization. People don't want to spend the time, but at least it's clear that you think it should have a higher priority, maybe. It's becoming more important as datasets grow in size. Yes, I think that's really true. How are you going to find out what's in your really big simulation if you don't visualize, at least for a summary, at least to get some idea? And the last one is a bit ambiguous. Right, so I guess it also depends on what exactly you want out of your visualization. You know, if your goal is to do PR, then you're not going to use an interactive visualization. But I still think interactive visualization is worth quite a lot if done right. Okay, so what are the biggest challenges in doing visualization? Okay. So one thing that I take away from this is that it's not just one thing, right? There's many aspects in this. This one is a really big one. Yes, you have software that you need to use or can use, and if it has a limitation, what the heck are you going to do? This one is, well, you can explore that, try different visualization types, and then you will get some experience into what works and what doesn't work. Again, could be something for you to do. Finding the right tools, well, Guillermo already showed some of the tools. I have a bit more. This one is an interesting one, making them stand out from the rest. Again, that's trial and error experience. Looking at what you like and copying it is a good suggestion. Comes very closely with doing aesthetically pleasing results. Yeah, this one, pre-processing data for visualization, is a necessary evil sometimes. And the lack of CPU, GPU power, well, there's ways around it. I'll show that later. Finding the time, yeah, that figures. Okay, final question, what would you like to get out of this presentation? Because I had some email contact with Guillermo before we did the presentation, and there is some overlap, and I'll try to navigate around it. But if you tell me what you would like to hear, and maybe I can focus it better. So you can answer a word here, I believe, or 2 words. It's a free format. And I might have to go home after this answer, right? When I cannot provide it. Tools, methods, value. Okay. Well, it's all very practically oriented, that's good, because I was going to go there. Orientation. Over, right. Strategies. Strategies into what? How to approach a visualization project, is that that type of strategy? Okay. Okay, useful. Okay. Well, thank you for all the answers. That's really helpful. Good impression, workflow, right. Okay. Okay, so I think I'm good. I'll stop this one. Thanks for the answers once again. So my goals for the presentation is provide an overview of separate visualization topics, focus a little bit on the practical stuff instead of the theoretical, but also inspire you to show you what is possible and what you might be able to use. So that hopefully that matches with the previous answers. This is one of these things that is overlap. Why visualization? Well, Guillermo already went into that. We're very good in seeing patterns or exceptions visually. You can interpret stuff visually much better than you look at numbers. You can place things into context, etc. So here's a nice example. These are election results in the Netherlands from 2010. This is for the Orthodox Christian Party. And these are the vaccination percentages throughout the country. A few years later, well, you can obviously, there is a correlation. It's not perfect, but when you're looking into a topic like this, a visualization like this always helps, right? But it's also a good place to start looking into, well, why are these parts of the country also, why do they also have a low vaccination rate? And this one I really like. This is from the Blue Brain project, which is investigating brain structures at the cellular level. So how neurons are connected through fibers, etc. And they make incredibly complex 3D models based on biological samples. And you have to visualize there to see what layer here is connected to there, how that works, in order to even simulate something like that. So you need visualization there. So once again, one of the use cases is just support your research activities, explore your results, do exploration, look at the simulation output to see if it's correct, communicate with your peers. And the other one is more for PR and communication purposes, because you can tell a good story, or engage your audience, or maybe stand out, right? This is something you use for journal articles, posters, maybe the group website, or a funding proposal. So like I said, there was some overlap. I had more of these in my presentation, I cut them out. This is one of the things I want to keep in, because if you do a good visualization that really talks to people, that really suggests something, wow, that's a cool story, then somebody like Bill Gates might pick it up and you get retweeted. So it could be a goal, right? Get retweeted by Bill Gates by your visualization. You mentioned this as well. You can misrepresent or suggest or lie with the visualization by changing the axis, changing the trend. So I'll skip this one actually. But sometimes you get something like this, right? EU referendum Brexit results, mad cow disease. Well, this is completely fake, right? They just took this image, then changed the colors to this. But this went around the world back then because people thought, what, is that really true? It cannot be true. So, well, you have to watch out with visualization always. Oh. Let's hope it comes back. Yes, there it is. So I would say there's a third use for visualization, and it's to inspire, to be creative, explore, etc. So this is what happens when you get stuck in a project and you get frustrated, right? This is the blood cell project that I'll talk about a little bit later. We're having some difficulties with the software, etc. And I just said, well, screw it. I'm going to go minions. Let's see if I can do that. Well, it turns out quite nice. This was actually a mistake that my colleague made. This is a simulation of a tornado, so the fluid flow, the airflow. And what he did, he by mistakenly plotted all the time steps in a single picture. So that's why you get lots of these arrows all together. But he was looking at that and, wow, that's really cool. I'm going to make that into something even more pretty. So he tweaked the colors and made it different and added shadows and stuff like that. And that's now his background on his laptop because he likes that. So he gets inspired by it. And I'll come back at the end. This is a 3D print of a 3D model. And it's really funny to see data that you normally only have on your screen in your hands. And it does something to you, to the feel of the data, maybe even interpretation on it. One important thing is to always adapt your visualization. This is something Guillermo already mentioned. This is the exact same data in 3 different types of visualizations. It's very functional, like you would normally use it for analysis. This is a little bit more pretty with shadowing and the gradient in the background. And this is more for the layperson, right? These are bubbles in a fluid, air bubbles. We showed this on a large screen in an animation at a conference. But you wouldn't show that there for the layperson, right? So you need to choose how to show things. Right, so Guillermo already mentioned the sci-vis versus info-vis. Well, I'd like to go a little bit deeper into that. Scientific visualizations where the spatial layout is given from the data, so there's a 3D or 2D positions are given. For example, it could be a brain scan that you lay on top of a simulation or measurements, right? These need to coincide, otherwise the results become meaningless. The one on the bottom right, I really like. This is a simulation of airflow around a piece of landing gear of a Boeing. This is from NASA. And the ISO surfaces shown here indicate whether there's turbulence, or how the air is moving. And you see there's quite a lot of stuff going on there. And of course this influences either the forces on this piece of landing gear or the energy used, the efficiency, etc. But here you don't really have a choice, right? This is where the turbulence is, so you have to show it there. However, even with scientific visualization, you do have some choice. For example, here's 4 visualizations of the airflow around an obstacle. Different methods. This is called glyphing, where you put a little arrow or something or a sphere at different points within the data set and you color them, for example, by velocity or scale them. It gives a indication, a visualization of what's happening there. Here's a different one, is where you make slice planes, you color them by the visualization magnitude. It gives a completely different approach, a different analysis of what's going on there. And this is another 3rd example. So here you let loose particles within this flow and then see how they follow the flow over time. That's 3 completely different methods with strengths and weaknesses. You have to make a choice, right, if you want to analyze this. So even with scientific visualization, the 3D spatial layout might be given, but you're still faced with the choice, well, how do I visualize it? And especially if you want to show multiple things within one picture. For example, you might have something on this flow, but you'd like to show another value as well. You need to be a bit creative. When it comes to information visualization, like we said, there's no spatial layout within the data. It's abstract, usually. So the small multiples already was shown, is where you have different graphs that you show side by side instead of in one picture. You can see different trend lines, for example, going up or having a peak. Graph data, so networks, is always a challenge. Right? You have things that are connected to each other and you can lay them out in a certain way, for example, here in groups that are connected. But you never know if that is that is the correct way to visualize it, because there is no correct way. Every layout that you do of a graph is equally good as another one, because the data itself does not provide you with a layout. Right? So here you really have to look into, how do I lay out this stuff? And what I'm suggesting, for example, these groups here, is that really true? Are these nodes really different from the rest? So graph visualization is really, really tricky one. Something that you'd like to do interactively. So some information visualization types work only well when done interactively. So here's the Pedalo coordinate plot that Guillermo already showed, maybe even the same data. So not sure. So every line is a single car, and for each car there's 7 data points, and the number of cylinders, the weight, the horsepower of the engine, etc. And by plotting every car as a line and then coloring them as well, you get some idea of the way this data set is organized. Here you can see an interesting relation, so what's high here becomes low there. Well, that's no surprise, because the more power the engine has, the faster it will accelerate from 0 to 80 miles per hour. So you get this twist in the lines. But you'd really like to flip this axis, right? So all these lines go like this, because then you might be able to see more. But that's typically something that you'd like to do interactively. You just like to click this axis, flip it, or maybe select a part here and see where these lines go. And have an example later on for this specific type of plot. So geospatial visualization is a bit of a weird one, in that it's usually information visualization that you're doing, abstract data, for example, density or number of votes that you're plotting, but you want to plot it on a map where the position is given. And that might be a problem, because the map that you're using might not have the best representation of whatever you're showing. So here's an example of how you can tweak that. So this is something to do with wealthy. Forgot what it is. What they did here with the map is scale up these areas for which there is a data point based on density of the population. So you can see that London becomes a large blob, obviously, because there's a lot of people there, right? So this importance of having many people in a certain area becomes suddenly visible, while here it's almost hidden. If you forget this, then there's nothing left there. But this isn't the real thing, of course. This is an approximation of the map. So within geospatial visualization, you might have to tweak that a bit. And one thing where I encountered this was when I tried to understand the Barcelona public transportation system yesterday. So this map, well, this is a known type, right? It's just a simplification of the actual thing. And then I read about the zones that you have to think about when you buy a ticket. And I didn't understand these zones, so I found this picture and thought, that's a lot of zones. I want to go from my hotel, which is probably here, to BSC. Which zone is that? So there was a lot of text and I didn't want to read it, so I Googled, and then somebody had made this picture. And I thought, now I understand. Almost everything is within zone 1, so we don't have to worry about the zones at all. However, these are not the metros, I found out later. These are different things as well. So. Some few examples of infographics. Guillermo already mentioned these. I really like these when done correctly. So population density in the Netherlands, shown as a 3D bar chart, which is based on the country. You can see Amsterdam and all the other cities in the Randstad are highly populated. I'll skip this one. No, I'll not skip this one. So what these are 5 music companies that produce CDs and that have artists working for them. And what this chart shows is there's a single K-pop band, so this is Korea pop, called BTS, and they have 4.6 million singles for this company, and the second largest company has, well, 2.5 million singles, but they need about 15 bands to get to that number of singles. So it's a graph within a graph, which is an interesting thing. So it really shows how big, how popular this thing is. Okay, you can use this for, well, a bit more serious applications. This is a nice example. This was when a story about the Indian Mars probe, and the story there was it was built really cheaply. It only cost $74 million US, which is nothing for anything you sent into space. So what they did, produced this graph, and within the graph are different space probes as well. And you can see, well, these are 2.69 times more expensive, but they also added some movies about space exploration to show how much that cost. I think that's an interesting way to attract attention. And this one is about how far we are getting in terms of Mars exploration. So it's not readable for you on this projector, but this is the time axis. So this is the 1960s, 70s, all the way to now. These different rings indicate up to what point we got. So this is, we managed to launch the probe. We got into a flyby, I think, into an orbit, we landed, etc. So it shows that as time goes by, we're getting better at landing on the planet and exploring it. And if you show that in a table, people would say, well, who cares? You have to be careful with how much complexity you put into an image. I like this one because it shows how a human embryo goes from a single cell all the way to a baby after 9 months. You can have some information about the different periods within pregnancy. But it turns out that this author actually also made this one. And now you start to question, why? Right? Because now you've got something moving, data moving along an axis, which is absurd. And if you want to follow something, you'd have to follow it all the way from there to there. So why not just have one of these embryos iterating over time? So this is a step too far, I think. And some other bad example, this is the genetic tree of life, all rolled into one. So all relations of everything we know about how life forms relate to each other. So it's a giant tree. Why? I mean, it makes no sense. This one I like because this is not so much about the individual data points, it's more about the story. So these are all known exoplanets. These are not telescope images because we don't know how these planets look. So these are all artist impressions. But the sizes and the types of planets are, well, somehow represented. So it gives you an idea of how much is out there that we don't know. So that's a nice visualization. And you can get too silly, of course. The year Robert De Niro stopped caring based on the scores his movies had. So they say, right, he didn't care anymore. Well, might be some forced interpretation there. You could put that line here or maybe here. And that one, yeah, I don't know. Okay, so to summarize, scientific visualization, you have a spatial layout, but you still need to think about how to represent that visually. Information visualization, abstract data, you need to do even more there. Geovisualization is a little bit in the middle, and infographics is more about telling a story within one picture, usually for the layperson. And then there's a thing called visual analytics, which is more or less what you're doing usually when you're working with visualizations. You're using visual representations of certain analyses to figure out what to do next, right? You want to learn something, you want to discover something, using visualization within a loop, and you're, as a human in the loop, steering that whole process. So the fact that visual analytics exists is not something that you use, it's just something to be aware of, that it has a name. And sometimes you find tools that say, well, we support visual analytics, and they do that in a clever way. So speaking of tools, well, what could you use? Well, you can't see it, but here in the background on my screen are all kinds of logos of open source packages. There's quite a number of challenges because there's a huge number of visualization tools and frameworks available, especially for information visualization. And it seems that new ones come out every month. Some new JavaScript framework, some new Python framework. There's some that are domain specific, so you might not be able to use them in your domain. And no tool will cover everybody's needs. And usually when you want to do more advanced stuff, you need to do a little bit of programming in Python, for example. So in order to get some idea, some selection of that, I figured to make some assumptions. So it must fit into a scientific workflow, right? A general tool if possible. You want to keep control over your data, because there's also a website where you upload your data and then do the visualization there. Well, I can imagine if you're doing research, you do not want to give your data to some weird cloud-based provider. If possible, programming scriptable and open source, etc. So this is very much like the table that Guillermo showed, just a bit more examples. I'm not going to go through all of these. I merely figured I could give you a summary of what I think are interesting tools to use and often used tools, so you can pick one and then look up yourself. So below the line is everything that's either commercial or closed source or limited. So Plotly, for example, is a web-based visualization, and this is all open source. Yeah, I'll just leave this in the slides, so we'll get the slides to you. So by the way, I don't have your tools here. I just added Photoshop and Illustrator after you mentioned it, because I don't use them. So my personal choices that I use a lot: Jupyter Notebook. I assume that you're familiar with it, otherwise we'll have a short example on that. Matplotlib is used a lot. Pandas, if you have a lot of data you'd like to, for example, time series that you want to work with. Leaflets for geospatial network X, and D3 if you really want to build something. And for scientific visualization, there's really not that many choices. It's either PeerView or Visit if you want an application. They do more or less the same thing, but PeerView has a much better user interface, and Visit is horrible to use, but still a very good tool. VTK if you'd like to program and really build your own visualization application. And Blender for making it pretty, and I have more information on that. So as a case study, I'll talk a little bit about simulation of blood, which is not the shining level of blood. It's these cellular levels of blood. I don't know, did you see Gabor Savotsky's talk on Wednesday? Some of you did, okay. Right, so that's the research that I'm going to apply these visualization things to. So one of their focus points is aneurysms, right? These weak points in the blood vessels within Combiomed. It's very clear division of labor, so the UVA does all the science, all the modeling, all the computation. They do a little bit of visualization, but most of that is on our side. So we provide the computer infrastructure, work on the visualization, and produce an animation that I'll show later. And I guess this is known to you, right? So you can take actual patient data, extract a 3D surface, prepare a mesh that you can use to do a simulation based on that. And these simulations are all cell-based, so instead of continuum-based, right? And as you probably also know, blood is a bit of a weird substance, so it's not a fluid per se, because there's, well, almost half of that is cells. And this gives the blood really weird properties, which is why it's important to simulate it. This is the Hemacell framework based on Palabos that the UVA basically developed this part. They have a really nice website, basically, by the way, on this project. This is hemacell.eu. Two types of cells, so the red blood cells and the platelets. The red blood cells have around 1,300 triangles, and individually these cells can twist and bend and rotate. So what I did here is I took a really small simulation of about 20 blood cells over time, and then took the blood cells one by one and placed them in a fixed position. So you can see the behavior of a single blood cell over time within that simulation. And this one is a nice one because you can see that it more or less manages to rotate while still keeping its shape within space. And this is something that's known from literature called tank threading. And red blood cells are known to do that in reality. So the simulation shows it, which is a good thing. But this is the thing that I did in Blender, and I'll show later on a bit more on that. And then when you have individual blood cells, you can put them together in the thousands, simulated on a supercomputer in this case. So each color block is one of the simulation domains, actually a core that computes part of the domain. And as the data moves from one domain to the next, there's communication between the processors to get all the data from one to the next. And as a whole, it computes the simulation. So it's periodic boundaries, stuff that comes out there, goes back in here, and it's a cylinder, although you can't see it. And there's quite a few cells of blood, quite a few cells within blood. So this is 2 cubic millimeters of blood. There's around 8 million cells for a hematocrit of 45. I don't think we're doing simulations at this level yet, because it's just too complicated, but it's definitely a goal at some point to get to these kinds of simulations. So lots of data. So this is a small one. It's only 6,000 red blood cells. 288 node cores, 500 time steps, so you get about half a terabyte of data out of that. It's not just the 3D geometry per cell, but also some per vertex values, like the forces acting on these cells, and per cell values, like pressure or volume. It's also saved to HDF5. So we've done that. Well, how are we going to analyze that? Well, for example, let's take ParaView. So I've loaded this one time step of this data here into ParaView. I don't know if many of you use ParaView at some point, or just one, two. Okay. So it's a graphical interface that you get. Each data set becomes one of these little items here in the tree, and on top of those items you can apply operations. So for example, I took the red blood cell part here, which is actually like this, and then clipped away half to be able to show what's underneath. On top of this is the fluid simulation, which has the same domain, and I use the streamlines here to start them here and then show the flow. The platelets are everywhere, and then I put in some slices to show what happens within the fluid. So this is the vorticity, if I'm correct, yes. And in this way you can interactively build up a visualization like this, and if you don't like what you see, you just change the properties here, or add or remove a filter, change the viewpoint, make the coloring different. And in this way it's a really nice approach into visualizing data like this. It even supports playback over time. If you hit the play button, it will show your simulation. Might be a bit slow though, because it needs to load in the data. I usually cannot hold it all into memory. So using ParaView has got some good points and some bad points. It's very good at interactively visualizing it. There's lots of ways of visualizing it, lots of options. So if you don't like the one that you're using, you might try a different one. There's also lots of operations. You can even compute, for example, gradients, or derive statistics from the data that you loaded, or program your own filters in Python. It can support time series and lots of data formats, and it's actively developed, which is a good thing. However, the GUI is, in my opinion, a little bit too cluttered. You're always fighting all these boxes and finding the right place to click something, and the whole workflow isn't very great. And if you happen to make a mistake that takes, for example, you start an operation that takes ages to compute, then the whole program is blocked and you can't really do something about it. But that was scientific visualization. Within analysis, of course, information visualization you use as well. So these are written out by the simulation code themselves at the end. So it's more like a dashboard that shows you the simulation health, if you'd like. For example, to check if there's no weird forces going on. Well, these are quite large, so there might be something going on there. Well, you could try to do that in ParaView, but it doesn't really work well. There is support for it, for example, for a plot like a histogram, or even plotting things based on position and the coloring. It doesn't really work well. So this is a point where you say, well, this tool isn't the best. I need to find another tool. So this is where the Jupyter notebooks come in. Well, you probably know this. It's a web-based interface. You have blocks in which you can enter code and then execute that code. And using the right libraries, you can get visualizations directly within the web browser. And in this way, you build up your visualization to see what goes on there. If you'd like to have a bit more interactivity, you could use a library like Bouquet, which gives you the same type of plot, but now you can actually navigate within these visualizations. So it's an easy way to get interactive visuals without having to program, really. Okay. Right, or if none of that works, then maybe you'd have to write something of yourself. So that's what I did here. So this is the Pedalo coordinate plot, like I showed before. This is for the per cell values of these simulations. So it's the forces, the angles, the position, etc. And it's basically an overview of the whole simulation. And put a slider on top that allows you to go to a certain iteration within the simulation. And you can get an overview of what the values are for the cells. And by selecting just a part of an axis, you can select a subset of the cells. It shows you where they are at that point in the simulation. And in this way you can try to analyze what's going on in your simulation. Now this is quite a bit of work to create this, because it involves programming with JavaScript and a bit of Python. That might not be worth it if you're doing just a one-off simulation. But say you're doing a PhD research and you're going to work a couple of years on a code and you will have the same data and the same types of analysis. It might be interesting to think about creating your own tool for this. So to summarize, depending on what you want, you need to look into different tools. The tools will never do exactly what you want, so each has its own strengths and weaknesses. I think trying them out is just the best way of getting to grips with that, and you might have to convert your data to a different format. So for example, what I did for the Jupyter notebooks is to convert the data to a SQLite database for easy querying of the values. Right. So visualization can usually be thought of as a pipeline. You have some number of data sources, you apply some filtering operations that, for example, cut out a part, or you compute some extra statistics, and then at some point that raw data gets transformed into something visual, right? Lines, spheres, etc. So that's the mapping part, and then it gets rendered on your screen, which is usually what your GPU or your graphics card does. So this is the way to go from data source to something visual. So what we see with people that compute at our site, well, you're using a supercomputer by choice, of course, but because you have a large simulation. So a lot of data will come out, and then what? Some people still try to copy that to their local laptop, right? Stuff that they computed on a supercomputer. You think, why? Because now you have to do everything in this pipeline locally. And the first problem usually is storing that data locally, right? It's a couple of 100 terabytes. And then every step is just worse and worse. So a remote visualization can handle these challenges. So the dataset become larger, issues for storage, your GPU might not be able to handle it, etc. And if you want to do interactive visualization, it becomes even worse. So the Jupyter Notebook is one form of remote visualization already. So you've got the server, could be running on the super or on a system next to it, has direct access to the data. A lot of the operations can be done remotely, and at some point it gets sent to your browser. So this part you don't have to do locally. And that already saves you quite a bit of compute power. However, depending on the type of visualization within the browser, it might still need to do all the rendering locally. So it could be that it's an image that is sent, but if it's sent over as a collection of spheres, then these still get drawn locally. And if you have 1 million or 2 million or 10 million spheres, it might still be slow. But this is already an improvement. ParaView also has a nice remote visualization capability. It's called the desktop delivery mode. It's where it's basically running the whole pipeline on the server side. So we run this on the super where the data is. You connect with the regular GUI client to that server. So you run this on your laptop. And everything happens here. And you can work within ParaView as you normally would. Building up pipelines, trying visualization, etc. And it's a really nice way. And the important thing here is that you don't have to run just one server process. You can run 100 or 1,000. If you, for example, have 1,000 GPUs in the super, then you can use 1,000 server processes. And ParaView will do the visualization and the analysis in parallel for you. But you may need to make sure that the data that you're using is already split up into parts. That's the downside. It will not do it automatically for you. So as an example, once more this blood cell dataset. So this was I think it was more of a test by the UVA to see, well, could we create initial conditions for a really large simulation? So they took 8 million blood cells and 0.5 million platelets, placed these within the domain without intersection overlapping. It took a week to compute on a pretty large system. Well, can we visualize that? Because I can imagine writing the code that does this, but then you need to look at the output. So I did a little test within ParaView. I chopped up this dataset into parts, so each file is a part. Cells, this does not mean red blood cells, these mean triangles in ParaView. So it's 10 billion triangles. We're using 128 nodes of the super. So this is about 1,024 processes. And you can see, well, it's not perfect, but it's better than not being able to do it at all. Right, so this is the actual data. Nothing is left out. You can inspect, you can cut the data any way you like. And here you can see the individual domain parts that are loaded in. So this is a really powerful way of visualizing these really large data sets. Okay, and then the final option that we offer at our site is just a normal remote desktop through VNC. This isn't visualization specifically, but you just run the CNC server here. All your application is running here, all the processing is here, and you just see a remote desktop on your laptop. And this is useful for applications, for example, graph visualization with Gephi. If you can do that on the GPU on a large graph, then the GPUs within the super will help you. Okay. So what are the use cases? Just to summarize, if you have limitations on your local system, if your data is already at the HPC system, why copy or move it at all? If you can do the visualization there. If you need parallel rendering for really large data sets. And the nice thing about the VNC is you can just have somebody else connect to the same VNC session and they will see the exact same thing. And you even get 2 mouse pointers that you can interact. So it's an easy way to share, to collaborate. But of course your local administrators need to install VNC, etc.
Question.
Yeah.
For this kind of massively highly intensive rendering, it's very, for example, the ones on HPC is very different from the render farms they use for CGI for movies and stuff. Is that one more specialized or this one? Yeah,
it's usually different. I would say that even for animation rendering these days, CPUs are still more used than GPUs because it's cheaper. And the requirements are different because in an animation you just render a frame, it might take a few minutes or a few hours and then it's done. But when you're doing interactive visualization, you want the results within milliseconds. So you get different GPUs, different interconnects between the systems, different network connectivity, yeah.
Also, maybe render engines for VFX are made for GPUs. So only recently, except from Blender cycles,
yep.
Only recently they are exploring making GPU-based.
Yeah. Yep.
For these massive ones, it will make sense at some point to just specialize. If it's already being done in HPC systems and supercomputers, it will make sense at some point to just, for example, this like you want to simulate a later plot, that will go be extremely expensive anyway, even for
I don't know. I would still expect a specialized supercomputer to be always more expensive than your run-of-the-mill cluster. And the cluster is still the way to go for animation rendering these days. Yeah, so I don't see those getting together. Okay. So I'd like to focus a little bit on the virtual human movie. I think you all saw it at some point. I will show just a short clip of a minute later on. So Guillermo with his team HBSD were in the lead here, right? So the goal was to be about 5 minutes. We have a lot of different simulations from the UVA, from UCL in London, etc. We need a script and we need an ID and we need direction, production, art direction, etc. And the SURFsara only works on the UVA cell-based simulation that I already showed. So the goal was to show this on an IMAX screen at the Science Museum London. It's huge, so we need to make it look good. which already makes it a different visualization than if you do like a functional one for analysis. And all kinds of inputs to this creative process, because that's what it is, right? It's not science. The science was done, you have the output, and now you need to be creative and produce something for it. So different things. Script is the story that you're going to tell in those 5 minutes. The art references were provided by BSC, and they suggested a certain kind of look or feeling to the images, and you need to match that, and it's kind of a challenge actually. So these are just images that they found somewhere or that they got out. And then during this whole process there was direction on lighting and materials. So can you make it look a little bit more like that, or it looks too red, can you make it less red? The camera is moving too fast, etc. And all the while we had these different animations. So, well, you need to think about what tools to use and what output you produce. And for our part, so the blood cell part, we use Blender. I don't know if you know this, but it's a really nice 3D animation package. Free and open source. It's been around for at least 20 years, I think, even more. And it's not just for animation, but you can do realistic rendering in there. You can extend it with Python scripting to do all kinds of interesting operations on your data. It's even, I would say, it's just good to, if you have 3D data services, for example, you can load it in and work on it within Blender. And it's very, very good workflow to be creative. But the immediate problem is to, well, get this data into Blender. So it's large, right? We have a number of terabytes in total for these datasets. And we did not want to convert that to a different format yet for visualization. So we'd like to read the HTML5 files directly. And luckily the scripting interface within Blender allows that. So we wrote a little bit of Python. It became a script. And the nice thing, it was a script with a number of options, so we could just fire up Blender, call that script, the set of HTML5 files to load, and then say, well, I want all of the data as a single object, or I still want to keep the parts, etc. So that's a really easy way of loading this data. So for example, this, what I call the cell wall, of putting a cell side by side, was just a flag to the script, and if I use that flag, this is what Blender loaded. And this was a bit of NumPy, some C++, and some operations. So that already gets the data into Blender, and well, it needs to have a certain look, and it needs to match the art references. So this is a bit of a challenge because you're battling between these three axes. So first of all, it needs to be realistic at some level. Right? So it's blood cells. You still need to look like blood cells, but actual photographs or representations of blood cells are either by electron microscope or an optical microscope. And these don't look very nice. But this is the way these things look in reality, right? But this is not the way we want to show it. You might have to use a certain functional style because it highlights some feature within the data. Might use color for that or focus. And then at odds with that is a visual style. Usually when you look up to, when you look into YouTube, for example, movies on red blood cells, they look like this. A very strange cell wall with all kinds of stuff going on. There's just a few cells there, nothing like reality, right? When it's full of cells. Or it might be cartoony. So here there's quite a bit of freedom, but also limitations into how to do this. So I hope this comes over nicely. So this is one way to just visualize these blood cells. But it's really flat. So if we add shadowing, this already becomes much better. And in fact, I would say this is so much of an improvement in terms of being able to analyze the structure, to see the, oh wait, let me kill this. This is better, sorry. Let me try this again. So without shadowing, with shadowing. Right, so this is so much better, even to analyze and to interpret the structures, that it's becoming now more mainstream to use shadowing. So this is what ParaView these days can produce with a different rendering option. Shadowing, nice lighting, you can see the structure, you can interpret the shapes. So this is becoming more the norm, even for scientific visualization, right? Because it just still uses a color scale to indicate velocity, etc. So what we ended up doing is creating a few different materials within the simulation. So we had a blood cell material, tissue, etc., and some others. Interesting thing about this is that you can see this white edge. That's not an accident or a happy accident. That's something that we deliberately did. It's called Fernell shading, and that highlights edges with a little bit of white, so they stand out more. But those are the really subtle changes that you use. And then to light it all, it was actually a star field that was surrounding this scene, because it gives an interesting type of light, which you can see here. So it's all little tricks to make it look more interesting. So this is with shadowing, and this is more or less what we ended up going for. So the less red, you can see the Fernell shading. Well, it's not realistic, of course, right? Nobody has ever seen red blood cells in the sun outside. But we need to pick something. And then there's the camera movements and camera angles, etc., for each of the scenes. This is really trial and error. So this is one of the first attempts that we did at, well, how can we move the camera? You can see it's a bit, it's not really great. There's some cells popping in and out. That's because of the periodic boundaries. The cells cross the boundary. They go outside of the view. For the simulation, that's not an issue, but for the visualization, it really is, because you can get these annoying things that go away, and people say, well, where did that blood cell go? So doing lots of tests like this to, well, to get further and further, and we need to render this at some point. So we used our super for this. I have no idea how it compares to Mare Nostrum, actually, but this is ours. So one thing to note is there's a set of GPUs in there that we can use. And if you render on a supercomputer, of course you have to go through the batch system. But that's actually not that difficult when we do a little bit of scripting again. So we wrote a Python render script that took a frame number and a set of options, so we could easily vary, for example, the camera or the quality of the image. And then we use a Slurm batch file to load the appropriate software, use an array job so we can get the frames all in sequence, and then render them all. And if we were lucky, we could render all the frames at the same time, if the system was a bit idle. So we'd get a whole animation done in a couple of minutes, otherwise we just have to wait. Interesting thing is, Blender allows fairly easy to switch between CPU and GPU rendering. And the GPU rendering is optimized for GPUs, obviously. But if we look at our system, there's two types of nodes in there. So the CPU nodes, we have a lot. We have a few GPU nodes. And the way these things are budgeted and accounted is a bit weird. So to the GPU nodes, we apply a factor of 3 to the number of cores. So that gives us 48 SBU, which is our credits, basically, that we use. So for each wall time, for each wall clock hour, we use, you charge 48 credits for the GPU nodes and 24 for the CPU nodes. So the GPU nodes are twice as expensive to use, which means that the rendering must be at least twice as fast in order to be cheaper. Otherwise, why do it? So I did a small test on that. This frame I rendered at this resolution, and it turns out that the GPU was only 1.7 times faster. So it ends up being more expensive. So we did not use the GPU to compute all that, right? So this is, but depending on the shading used and the lighting setup, this might change. Certain things work better on the GPU than on the CPU, so this really needs a bit of testing. So we had the event in London at the Science Museum late. It was quite nice with some discussions and the movie on the big screen. And I have a 1 minute clip of that. It's not just our work, it's got a little bit in the beginning and the end, but it focuses more or less on the blood. And I know you've seen it, but I'm going to show it anyway. Yeah. So we did make this one. This is just a static model where the camera movement needed to be nice. It's very small wiggling. This is from Germany, I believe. So the really nice thing here I like is that this is the actual simulation data, right? This is not an artist that created this. Circle of Melis. So you can see this metal that works very nice. Of course, the metal doesn't look like that in the body, but it's a good suggestion. Right. Right, okay. That's enough. So we learned a lot doing rendering and animation with Blender within this type of data. And we thought, well, maybe other people would be interested in this as well. So this is a course that we started last year. We had it twice within Praise. It's a full day course of using Blender for scientific visualization. We had quite a number of people there. I think we had almost 60 over those 2 courses. And it goes into the basics, how to get your data into Blender. Maybe you'd like to do a little bit of editing. Then we go into the lighting, materials, rendering, how to make it look nice and do a little simple animations. So this is the course. We have a next edition planned on May 21 this year, so in a couple of months. It's in Amsterdam, of course. And I believe the website is already open. So if you'd like to follow this course, then you can register already, I think. Let's see. I'm going to skip most of this, but just wanted to show you this picture. So this is this 2 by 1 by 1 millimeter blood cell block. And the interesting thing is, when I was doing this visualization, I actually did it wrong the first time, because these cells are supposed not to intersect, because that's what the computation did. And I'm still not sure I got the correct visualization here, because I cannot check all these cells manually. I cannot look at all cells and see if they're correct or not, but occasionally I still think, did I do the visualization correct? Because I wrote a little program that took the original data, reconstructed the 3D data set, and then done the visualization. And I might have made a mistake there. So even when using visualization to, let's say, check simulation output, there's a bit uncertainty when you start doing things yourself that aren't tested yet. So I thought it was interesting to realize. So the visualization isn't right all the time. And another thing that we see with visualization is we always have to match what is there. So for example, in this case, we had the UVA that already did simulation, saved it in this file format and used peer review to visualize it. And they start talking to us, well, we've got this Combiomed project, we're making this movie. Can you help us make these animations? So yes, we can. We'd like to use Blender. We can read your files, but we'd need some extra stuff like different scenes for cameras, materials, the animations, etc. So we added some things. And then they said, well, what comes out of the animation is PNG. We make a movie out of that with FFmpeg and we send it to the BSC guys to check it. But then the BSC guys said, well, we'd like to have it in a different format because we cannot composite this. And compositing is putting the movie together in the right shape, basically. So we used a different format. These files were really big, so we needed to use SURFdrive, which is like an own cloud that we use. Well, you can see where this is going, right? For every type of visualization, more and more stuff gets added. And this is unfortunate, but maybe also the way it is. Because at the end of the day, it's the UVA researchers and whatever visualization they need that we do the work for. But you can see all this stuff around it. We're using VTK or the Jupyter notebook for the different analysis, and it needs a different file format, etc. So I'm not sure I have a point with this other than complain a little bit. Okay, so for the final part, I'd like to focus on something completely different. So I mentioned that we do this innovation type of work is where we look at the different devices that are out there, different types of visualization. I figured I'd just show you some for inspiration. So I suspect most of you will have had a VR headset on at some point in time, or maybe not. Who has had a VR headset on his head at some point? 1, 2, 3, 4, okay. So there's a whole spectrum, right, of providing virtual environments. And the most immersive one is VR, which is where you have a headset on that fully closes your view. You see only the screen in front of you and nothing of the real world. And then we have augmented reality, is where you have screens in front of your eyes that you can look through partly, and the device overlays something on top of reality. But there's also something called mixed reality these days, and it's a bit of a marketing thing. And they say that the difference between MR and AR is that with MR, whatever you put into the real world virtually stays in the right place. So when you move around, it doesn't move along with you, it moves right. And then we have extended reality, which is basically the whole thing together. Now, I don't care about all these terms other than VR and AR, and that's the two I'll be using. So a couple of years ago, we bought this HTC Vive headset. The way this works, you get these little boxes that you need to hang up in your room, about 5 meters apart. The device can sense where it is in relation to the boxes, and as you move around, the image is adjusted. So we made a small example, a demonstration example for that, of visualizing CFD simulation. So you can see me moving around here, and this is what the headset itself is showing. So this is from OpenFoam. If you use OpenFoam, you've probably seen this one at some point. This is from the tutorial. And what this does is allows me to place these streamlines at some point. Here we go. And say they start here, and then how's the flow go from there. Right, and you've really got this motorbike in front of you in the real size. And it's a quite interesting way of visualizing this data, because you could do this in pair view, right? No problem. So what's the point? Well, you do get a different feel for the data, because you can put your head in any place that you'd like. And something that I found while doing this was, hey, within this part behind the windscreen, there's all kinds of turbulence going on. And I might not have seen that or explored that if I just used pair view. But by really going in there with your head or with your arms and then trying it out, you still get a different feel for the data. But you don't have to show it one by one, full size. You can make it smaller, because the simulation domain is, I believe, 12 meters or something. So you'd like to have a table view as well. That gives you more context. You can inspect the simulation domain and see that there's more detail in the domain here than over there. So all in all, it's an interesting exercise. But the downside of VR in its current form with these headsets is you're really closed off from the real world. Right? You bump into things sometimes because you don't know the chair is there. The field of view is okay, but not perfect. You've got these controllers in your hand, but you really like to use your hands just like that. And some people get nauseous just by looking at things like this. But the good thing is, you can show fairly complex 3D worlds. It's immersive, like you're really there. And these headsets are fairly cheap these days, just a few €100. So it's interesting, but content and application-wise, it's not too good. Right now there's a lot of games. Pair view has some support for VR. Yeah, you can use it. But the real big issue is the market going to accept any more VR headsets, or is this technology going to go away? Because it's been around for a couple of years already. Right? We have different iterations. The headset got cheaper and smaller, but I don't think it's going to take off anymore. I think this is it.
Maybe for medical reasons, in order to ensure that complex treatments or operations are actually
Sure.
precise. I think that's a huge market there that
Yep.
isn't still developed.
That's a good point. But what you see is I'll come back to that later, is that AR is taking over that part and not so much VR. So this is my personal opinion, and some of my colleagues, we think VR is not going to make it, basically. Because AR is slightly more interesting. Now, there's different types of AR. This is a test that we did with an iPad using ARKit from Apple. And what this allows you to do is just, when you hold the iPad in your hand, you look at it, and you place data on the desk, for example, and it stays in the place where you're placing it. So even though if you move around, well, you can see it sliding a little bit. But this is just using a regular iPad, right? Everybody has it. So it's cheap to do. It takes a bit of programming, but it's not too bad. And this ARKit from Apple is free, so you can just download it and get working. And it's an interesting way. Right, so it's already better than just looking at your screen. But you have two hands on the iPad. If you want to press a button, you've got to let one hand go, and the iPad starts doing this. So it's not very good. The graphics implementations on the iPad are not too bad. You can do fairly complex models as well. But you won't store a really large data set on the iPad because it's not good for that. So I'll spend a bit more time on the Microsoft HoloLens because I think it really has a bright future. These came out a couple of years ago, so-called wearable smart glasses. So you have them on your head, you see through, and you've got your hands free. And it shows you what they call a hologram in front of you. Well, it's not really a hologram, it's just a marketing term that Microsoft chose. And it's a full standalone device, so there's a full computer in here, including a special processor for the tracking and the interaction. Was a bit pricey, it's a little bit less expensive right now. And it's running Windows 10. That's basically all you need to know. Oh, it's quite heavy, so it's almost 600 grams. So you can wear it on your head for an hour, but you'll feel it in your neck at the end of the day. So one of the really nice things about the HoloLens is it's got all kinds of sensors in it to see the environment. So it's got a number of cameras that look around. It's got an inertial measurement unit in there to keep track of the movements. A special purpose, what they call HPU, the holographic processing unit, is a chip that integrates all of that stuff in order to have the HoloLens see where you are within the room, but also see where all the surfaces are. So it can see where there is a couch or a table or the floor. And you can use that to put something on a surface virtually. And it also has a camera to allow you to see your hands and interact with it. So this is more or less what it looks like. I have a movie later on. So we've got our room with a virtual model in there, and if you walk around, the model stays in place. The displays are not very high resolution compared to, for example, the VR headsets. So 1200 pixels times 720 per eye. And then the field of view is very narrow, so it's green. So you see only something there. But for now it's good enough, actually. So I thought, well, I can try to port this demo that I have in VR to the HoloLens and see if that works, if that's any better or not. But the HoloLens is a bit limited in terms of the complexity that it can show. Right? So the iPad can do many more triangles than a HoloLens because it's all in there. So only about 80,000 triangles, which is nothing. So I have to simplify the scene. It's not powerful itself, so I have to offload the computation to a server. There's no controllers, although you could use an Xbox controller. So we have to use the few hand gestures that there are, etc. I'll skip this. So this is what it ended up being. So it also has voice commands, which is quite nice. You can talk to it. So here we have a different CFD simulation. This is also from OpenFOAM. You can change the representation. With a smart menu, you can do these kinds of gestures to click. And what I did here is you can click twice to define the streamlines. The server computes the streamlines in real time and sends them back to the HoloLens, and that shows them. So it's a bit like the VR demo, but I'm in my room. That's the big change. I'm not away into some lab where I have to wear a headset that fully closes me off. And I have my hands free. Using a slice plane, colored by velocity, etc. So that's about it. So I worked on this for a couple of weeks, and then I thought, well, what did I learn? Well, I was really surprised about how much I liked it, because I thought the HoloLens was just a weird thing with a very limited field of view. How useful could that be? But I actually became a big fan of it, and I started to wear it a lot. I even took it home with me. I was programming with the HoloLens on it. I was getting hungry, so I went into the kitchen, and I was baking a hamburger, and I still had the HoloLens on. I think, that's natural. I'm not even taking it off, because it's so natural to have it there. So that's why it's in my kitchen here. So it's not as obtrusive as you'd expect. I hope it gets lighter at some point, but right now it's not too bad. And you really get this augmented reality. Things that you place somewhere in the room are still there when you walk out the room and come back. So that's really good. And you can place data there or a 3D object or whatever. And the voice input is very easy to use. So if you do programming, this is C#, you just use the word that you want to recognize and then the code that you'd like to call when that is recognized. So it's really easy. It's much easier than to build a GUI interface. You just use these voice commands. So there was things that surprised me. And this one was really surprising, because you don't think that the HoloLens would work outside. Well, it does actually pretty well. So this is at SURFsara in our backyard, basically. Same application, and it managed to track my position and my orientation fairly well. And we see now researchers within the Netherlands using the HoloLens to do outside research. People just wear the HoloLens, they get guided, for example, to a certain point, or they show obstacles on the ground that a person has to walk over, virtual objects. So the HoloLens has many more uses than you would expect in first.
Table?
Right, so it's got the tracking wrong here, it's a bit too low, but anyways, it's not too bad. Okay. So, some other good points. You're still connected to the real world, which is nice. Sitting behind a desk, you put on the HoloLens, look at something next to you, put it off, and go on working. No nausea. You still get your hands free, etc. The spatial tracking detection is really good, and it's a complete standalone device. So you upload the application to it, and that's it. And then the bad at this point. So the graphics are limited, small field of view. The voice input is nice, but if you're not an English speaker, not an English native speaker, your accent might actually interfere with the recognition. And your colleagues are always making fun of you when you're wearing it, right? What is that? And can I try it? And you look silly. And then the ugly, well, the hand interaction is very limited, just this or this. That's basically the two things you can do. You have to use your head more or less as the mouse cursor to focus. So you get a little dot in your view, and you have to navigate that dot with your head onto the menu. So you get, your muscles start to hurt after a point. And using UI and 3D is always a problem. Skip the Unity. So my conclusions for now is that the HoloLens has a lot of potential, much more potential than VR, because of these things combined. But it needs to improve, right? A better field of view. You'd like to have a field of view like this, natural hand interaction, better graphics. And the interesting thing is Microsoft is rumored to announce the new HoloLens version in about 2 weeks at a conference. And if it's going to be as good as we think it is, I think you can see HoloLens everywhere. Because if this thing is maybe $1,000, everyone is going to jump on them. You see the HoloLens being used within companies already a lot for training purposes, for example, or to overlay data in a warehouse. If it gets any better, it will be everywhere. And for science, it offers, for scientific visualization, it's really interesting as well. Okay. So 2 more exotic things. First one is the looking glass. I don't know if anybody saw this at some point. There was a Kickstarter last year. This model costs 600 euros, so not too bad. And what it is, it appears to be just a big block of glass with a display behind it. But it's really clever. It's based on your position, you get a different view, so you get a different image, which means as you move around, you can see something else. So here I've got a 3D model being shown. You can see this with depth, so it's stereoscopic as well. So it's really nice. And right now the resolution isn't too good. You can see that, you can see the pixels. So it's about 800 pixels times 500 for each of the positions that you're in. But there's 45 positions that you can generate an image for. And that's quite convincing. And the way this block works that's on top of it, it really makes it look like the object is within the block, and it's a kind of interesting effect. So it might not be usable for real, let's say, analysis purposes at this point. But it's definitely when you put it on like a conference or something and you have some nice content in there, people will go, wow, what's that? And how did you make that? And the way to make that is to simply render out these different views. So this is 5x9 views. Might be hard to see, but this is more on the left, and as you go up, the views become more on the right as far as the camera goes. So you render those views into such an image like this, and then you can display it on the HoloLens. On the looking glass. So not too difficult. So it's an interesting. I hope they bring out a new version at some point. They have a bigger version, which is $3,000, which is a bit expensive, but anyways. So the resolution is the main improves. And then finally, we looked into using 3D printing for visualization. So as you probably know, 3D printing has been around, really grew in the last couple of, let's say, 10 years for this maker community, where you make your own iPhone, what do you call this, holder, basically. Or you make jewelry, or you make a cup, or whatever. So the technology is there, it's not really expensive anymore. You can have a 3D printer for a couple of thousand euros, or maybe even 1,500 only. So can we use that for visualization? Does it make sense? What are the limitations? What are the possibilities? So we have this 3D data print project that we did. We partnered with a number of research groups from the University of Twente, with the UVA and some others, to see, well, let's take some data, try to print it and see what we encounter. And we did not do the 3D printing ourselves. We used a commercial provider for that, because one thing that we found is owning and operating a printer is very much time-consuming business. You have to change the material, you have to make sure it doesn't break, you have to start a print and then monitoring it over a couple of hours, etc. So we didn't want to do that. So we used a company called Shapeways. It's where you upload the 3D model, you get your credit card, and 10 days later you get the print on your desk. And I'll show some examples, but if you'd like to see the real report, which has got many more details, the link is there. So this is one from University of Twente, so it's a simulation of fluids. This is the normal visualization within Visit, using 2 ISO services. So this is cylindrical domain. It's basically 2 cylinders like this, right? And the inner cylinder is rotating. It's a certain kind of turbulence simulation. And this fluid trap between those 2 cylinders gets all kinds of interesting turbulence phenomena. So we took the ISO surface and then tried to 3D print it. And I wanted to 3D print it in such a way that you could see the domain as it is, but also in the separate parts. And this takes a bit of creativity, because the ISO surface here you cannot print directly, right? It has no thickness. These stands were not there. So that's one of the things you find quite quickly, that a 3D model that you have is not directly a 3D printable model. So this step from that to that can take quite a bit of time. Different turbulence example. And this turbulence is really fine, so you can see all the detail in there. And that's one of the things that we were surprised by how much detail you can print these days. This is really small, because a plane like this is about 20 centimeters. This is a big print. It's a keyboard, by the way. So you can see how big it is. And we had to print it in parts, because each part that you print only can have a maximum amount of geometry in it, and it's usually about 1 million triangles. Any bigger and you need to split it up. So even though you can print a lot of geometry detail, you still have to split it up. But it's really nice because the researchers that normally work with this data on the screen, they saw this print and they were like, wow, that's cool, and they picked it up and started looking at it and they thought, well, maybe there is something going on there, maybe it has an added benefit. Example from the UVA, where they did an arterial flow simulation of a vessel with an aneurysm. And the idea was that they simulated the vessel without the aneurysm first. And then looking at the simulation, at this cross-section, you look at certain values and see if you can predict that the aneurysm is going to be there based on those values, right? So I won't go into the details, but the idea was, well, we'd like to have this vessel and then have discs that are colored like this that you can place there and change them, for example, to see if that works or not. Now that turned out to be really a challenge, because printing something in color basically means there's only one material that you can use. It's sort of sandstone material. It's very coarse, it's very heavy, but it's also very brittle. So I had to make all these parts very thick in order not to break, and even then stuff broke. And sliding in these discs was impossible. So we just fixed the disc to be one color. It's this one, I think, at different positions, and you can look around. It's not perfect. So this one, I think, well, it's not great. So some conclusions from the project. Well, like I said, you can do much more detail in 3D prints than we expected. A lot of the researchers were really like, wow, that's cool, see my data and hold it in my hands. It was an unexpected effect. It's a natural view. Well, you don't have to worry about your GPU or your memory. It's there, you don't need a computer, it won't crash. It's stereoscopic as well, and it allows you to feel and use other senses. And all in all, the costs are not too bad. Most of these prints, for example, this one, I think it was about 80 or 90 euros per part. So it's not cheap, but it's not really expensive either. And then the limitations, well, you've got the limit on the amount per printable part of 1 million triangles. Color is very difficult to use properly. It takes a lot of effort to take the 3D model that you have and turn it into a printable one. So all in all, I would say it's interesting, mostly from a PR perspective. It's not going to be a tool, and it's not going to replace visualization as you know it. Okay, so that's everything I had to show you. I hope you enjoyed it, and thanks for the attention.